Hello again. So welcome back to our latest lecture session. So first again a couple of minutes to understand what we have been up to in the last session, right? So in the last session we looked at what do we say, a couple of minor what do we say, derivations, where we tried to understand the system, right, say, and relate P in terms of let's say molar Gibbs energy of the electron for a particular redox couple, and again to be able to relate that to the redox potential, right? So we were able to do that, and then we went ahead and looked at, I guess, two half reactions at the standard states and non-standard states, and try to understand that, let's say, as in terms of both the P values or looking at the molar Gibbs energy of the electron in each of those redox couples, to be able to understand, let's say, in which particular direction would the what do we say, reaction proceed, as in which half reaction would proceed as reduction, and which one would have to be oxidation for the redox process to go through, right? So in that context, obviously we looked at the case that the electron obviously would want to travel from a higher energy state to a lower energy state, right? So obviously I guess once this electron transfer, or during this electron transfer from higher energy state to lower energy state, so what are you going to observe? You are going to obviously observe a release in energy, right? So obviously what we are driving at here is that in this or during this what we say transfer of electrons, right, and because the electron is or was at a higher energy state compared to its destination where it's at a lower energy state, you are going to have a release in energy, meaning when this redox process goes through, let's say, right, you are going to have a release in energy, and we can calculate that too. So let's again look at the example that we had earlier. So this was the example at non-standard conditions, right? Non-standard conditions. The non-standard conditions were at pH 7, and that the activities of HOCl and Cl minus were respectively 10 power minus 4 and minus 3, but for the couple of SO4 2 minus and H2S, it's they are 10 power minus 3. And then we understood the system and saw that because the energy of the electron, let's say, or molar Gibbs energy of the electron in the couple or with respect to the couple SO4 2 minus and H2S is higher than the one with HOCl and Cl minus, or the one in equilibrium with HOCl and Cl minus. We know that the reaction or the electron would like to move from this couple to here, right, or this couple, meaning this particular one will go through as reduction, right, because it is going to accept the electron obviously, and this is going to go through as oxidation because it is going to release or donate the electron, right. So here as you see again there is going to be an energy release, so we can calculate that. So delta G of that particular reaction is going to be equal to what now, right? It is going to be equal to minus 120.48, which is the final state, right, minus 20.96, right, and that I guess is approximately equal to 141.4, and the units as written here were kilojoules per mole, right, per mole, right. So whenever there is one electron transfer, electron transfer or 1 mole of what we say electrons transferred here from the couple SO4 2 minus and H2S to HOCl and Cl minus, 141.4 kilojoules will be released during that particular redox process, right. So I guess that helps understand the system in a slightly better manner too, right. So we will now move on to the EH approach, right. So until now we have discussed the aspects related to PE and so on, right. So we are now going to look at the EH approach, I guess, right. So this is relevant to your electrochemical cell, EH approach or the redox potential, let's say, right, electrochemical cell, and let's look at what some of these components are, right. So you will have the electrodes, right, and the electrodes are cathode, where you have the reduction taking place, and anode, at which you have the oxidation occurring, I guess, right, and then you will also have your electrolyte solution, right, and then more importantly you will also have this salt bridge, I guess. Let us see the relevance of this within a short time, right, salt bridge, pardon me, right. So electrochemical cell, let us just try to visualize what we are up to here. And so let us say here we have our cell and our electrode here, cathode and anode, Let us say we have a semi-permeable membrane, or if it is not semi-permeable, we need a salt bridge, and we will discuss again why we need that. And let us say this is the cathode here at cell 1, and this is the anode here, right. Cathode is where the reduction is occurring, right. So, the electron transfer will be from the anode where the oxidation is occurring, as in the electrons are being released, right, and through the conductor, right. And we also need to have the external circuit. That is something I missed writing up here. We are going to have the external circuit, right. And why do we need this external circuit? Because you need a conductor for the electrons from one electrode to the other, right. So, here this is the external circuit, and obviously without this external circuit you will not have what we say the electrons being conducted from one cell to the other, and the redox reaction will not go through, right. So, now let us just try to understand the relevance of all these what do we say aspects that we looked at: electrodes, the solution, salt bridge, and external circuit, I guess, right. So, electrodes, I guess there are two kinds, as in the reactive and the non-reactive. Reactive as in these electrodes themselves take part in the half reactions, let us say, or are involved in the half reactions. So, over time you will have loss of these electrodes, let us say. The non-reactive electrodes, similar to let us say the platinum electrodes, let us say, are non-reactive, and I guess they just act as let us say the media, not media, I guess the surface at which the relevant half reactions occur now, right. So, again we have reactive and non-reactive what do we say electrodes now. So, again then we have the cathode and anode, right, this at the surface of which they themselves are involved in the half reactions, yes. So, at the anode you have the oxidation, the electrons are released; at the cathode you have reduction, electrons are gained. So, anode and cathode, but how do the electrons go from here to there now? So, that is the reason why you need the what is it now, external circuit, I guess, right. So, you need the external circuit, and obviously without the external circuit you will not have a redox process go through, right. So, that is the key one aspect. And again, just because the electrons are being transferred now, does that mean that the redox process is going through, or are there any other issues we need to consider now? The issue is that now there is going to be a charge imbalance now, right. So, the electrons are being transferred, right. So, there is going to be net what we say increase in the negative charge in your let us say the solution on the cathode, I guess, right. And then what is going to happen now? Again that will what do we say dissuade the redox process from going through. So, for that I guess you are obviously, for the charge balance to occur, you are going to have to look at the salt bridge or have a semi-permeable membrane, let us say, right, when let us say where that would allow the what we say transport of the relevant salts or the cations and anions, let us say, such that there is a balance with respect to the charge now, right. Again there are different cells, as in different kinds of cells, as in both the electrodes in the same solution, or electrodes in different what we say cells or solutions, pardon me, and so on, different configurations. But the major aspects are the need for the two electrodes, the external circuit, and the salt bridge, I guess, right. So, these are the aspects. Again, one aspect here is what is the relevance of these what do we say electrodes or these cells or such, let us say. So, let us look at one particular example, right. We are going to consider a case, let us say, where we have water in equilibrium with water, not water, pardon me, the atmosphere. So, we have oxygen and hydrogen in the gaseous phase, and let us say they are going to be now at equilibrium or in equilibrium with your water. So, you are going to have O2 in the aqueous phase and O2 in H2 in the gaseous aqueous phase, pardon, right. We have O2 in equilibrium with the aqueous phase, again H2 in the gaseous phase in equilibrium with the H2 in the aqueous phase, gaseous and aqueous phase equilibrium. So, again now as we know we have relevant half reactions, right, and if we look at the relevant overall reaction, I think we know that O2 plus 2H2 can lead to formation of your H2O, right. So, this is one reaction that can occur, right. Let us look at what are the conditions required for that to occur now. As we know, this reaction occurs only when there is an electron transfer now, right. And for that to occur, what needs to happen? Your O2 molecule, right, needs to collide with the H2, right. The aqueous forms of both O2 and H2 need to collide for the electron transfer to take place. Again, let us say O2 and H2, right. So, this can obviously sometimes what we say create issues, not sometimes, I guess, what do we say create issues with the kinetics, let us say. So, instead of that, let us say if I have an electrode, let us say a platinum electrode, let us say, right. How will this assist in furthering this particular reaction now? As in the relevant half reaction with the oxygen, let us say, can occur here, and the relevant electrons, let us say, can be transported to the oxygen molecule from here, while the relevant half reaction, right, with respect to the H2 and H plus can occur out here, and the electron can transfer through the conductor, let us say, or obviously the electrode will act as a conductor for the electron transfer. As in now you do not need the O2 and H2 molecules, let us say O2 aqueous forms of O2 and H2, let us say, to collide, or there need not be any physical collision now. So the reactions or the half reactions can occur at different places on the surface of the platinum electrode, and the electron transfer can take place from the site of what we say the H2 related half reaction to the site of the O2 related half reaction now, right. So this one obviously now promote the relevant what do we say overall reaction. This is just by one example. So obviously though if we get look at such particular cases though, we cannot, let us say, constructively utilize this flow of electrons from one what do we say redox couple to the other though. Let us say if you have your battery or such, what are we trying to do? We are trying to constructively utilize the what do we say current, or let us say the flow of the electrons, let us say, right. So to be able to do that, obviously you are going to have, let us say, two electrodes, let us say, right, two electrodes, right, again cell 1 and cell 2, let us say, and you have electrode 1 here and electrode 2 here, and now we have separation of the two what do we say half reactions. Instead of the half reactions occurring at just the on the same electrode, right, we are now going to have only one half reaction at one electrode, another half reaction at another what we say electrode, and you are going to have the transfer of these particular electrons here from one cell to the other, which depending upon the relevant redox process and the relevant energies that would be released, let us say, right, you can utilize accordingly constructively now, right. So here again the aspect that we need to look at is what drives this reaction now, right, the redox process or this transfer of electron. Again keep in mind that everything in nature out there, or the reactions involved out there, see to it that the energy of the system decreases now, right. So in that case again what is it about now? So the reaction would only go through when there is redox disequilibrium, right. Only when there is redox disequilibrium, right, where let us say the electron transfer take place from one couple to the other now, right. So but when the equilibrium is reached, right, what does this mean now? So for example, let us say you have redox disequilibrium and they try to approach each other, right, and now when there is equilibrium now, there is no more potential now, right. So there is no more potential now, yes, there is no more potential, and thus no more what do you say transfer of electrons, right. So obviously let us say for your electron transfer to occur, obviously the system needs to be at redox disequilibrium. Once the two cells reach equilibrium, let us say, right, you are not obviously going to have any further transfer of electrons. Let us look at the previous slide to help illustrate this. So here let us say you have what do we say EH here, right, the redox potential for what do we say one cell, and let us say redox potential for cell 2 now. So how is it going to go through now? That both the potentials are, they will travel in such a direction that both the potentials are going to be equal now, right. So one the EH1 is going to decrease and EH2 is going to increase, and once this EH1 is equal to EH2, what do we have now? We have redox equilibrium, right. So once again when we have that EH1 is equal to EH2, right, we have equilibrium, and then no more potential and no more transfer of the relevant electrons, right. So again this is the whole aspect that we need to keep in mind. Again, as in one example we can consider is your batteries, right. So what do you mean by when a battery has exhausted or is useless now, right? It means that the redox equilibrium has been reached, right, and you have and there is no further potential driving the transfer of the electrons, I guess. So now we are going to move on to the relevant aspects now. Okay, so let's again moving on, I guess, right. So one particular aspect it's worth discussing here is to be able to calculate or measure EH, I guess, right, redox potential. How do I do that? People look at the standard hydrogen electrode, let's say, right, I guess hydrogen gas at 1 atm pressure, right, and the relevant half reaction, let's say, and in reference to this standard hydrogen electrode you try to measure the potential of your particular or redox potential of your particular cell or the half reaction. So based on that you can calculate the relevant EH of your particular cell now. Usually carrying this or standard hydrogen electrode, maintaining that might be relatively different. So even if you do not have the reference of standard hydrogen electrode, which we set to be, let's say the EH to be 0, let's say, right? That's the reference here, let's say, similar to your mean sea level now, right? The standard hydrogen electrode, let's say. But let's say if you, most people might have used your pH meter, right? What's that measuring now, right? It's measuring again the potential there, right? Again, if you are measuring the potential, you need 2 electrodes again, right? So one electrode would be this, the standard calomel electrode, right? Where you have, I believe, HgCl2, the solid, right? You know, don't take my word on that. You have the standard calomel electrode now. So you know, you have within the pH meter your standard calomel electrode, and let's say the other electrode would be, let's say, in your solution, let's say, where you have, let's say, semi-permeable membrane where H plus would tend to, what do we say, be adsorbed onto the surface of the membrane, let's say, or this semi-permeous membrane, and then you are going to again measure what is it now, the potential difference between the standard calomel electrode, right, and the half reaction at the other platinum electrode. So when you dip your pH meter in your solution, what are you measuring? Again, you are measuring the potential difference there, right? So again, you are measuring the potential difference and calibrating that at pH 3, 7 and 11 and so on, right? And you are telling the system that, or the pH meter, that at this potential difference it's equivalent to 3, at such a potential difference it is equal to 7 and so on. So that's how you end up measuring your, what do we say, your pH, I guess, right? So again, you know, just an illustration, I guess, of where we come across this particular concept. So again, when we dip your electrode, what do we say, your pH probe into your solution, in effect you are measuring the potential difference between 2 half reactions there, right? Anyway, standard calomel electrode, but or standard hydrogen electrode. So reference electrodes to be able to measure your redox potential of your particular half reactions, I guess. So moving on though, we come to a standard equation, which is the Nernst equation for each cell, okay, or for each half reaction, I guess. And this is something that people might understand once it's written down. EH equal to EH naught minus RT by NF natural logarithm of Q dash, right? So I guess once we write this down, you should immediately be able to see the analogy with respect to PE is equal to PE naught, right, minus 1 by n being the number of electrons being transferred, natural logarithm of Q dash, right? And again, earlier we looked at the relationships between PE, EH and molar Gibbs energies of the electrons in the last session again, right? So again, looking at the same principle, or we can even malplate this again here, I guess, or if I malplate the first equation, this equation as EH into F by this value will be 2.303 RT, let's say, will be equal to again EH naught into F by 2.303 RT minus 1 by n log, it should not be natural logarithm here, it is logarithm here, right, log Q dash. That is the reason why we have the 2.303 value here, the PE1 with respect to the logarithm and not the logarithm to the base 10, not the logarithm to the base e. That was a minor error there. So here again, we looking at this, what can you understand here, I guess, right? You can understand that the PE value is nothing but equal to EH into F by 2.303 RT, right? Again, this is something similar to what we looked at or derived in our previous sessions here, right? So again, you see that, you see the relevant analogies, right, and from that we can understand the system again, and this particular equation is called the Nernst equation for each cell here, right? And here these are the redox potentials that people use or look at here, right? So again, let's moving on. So you have 2 cells here, let's say EH1 and EH2, let's say. So how would this particular reaction proceed, or how do I understand this particular system, let's say, right? So let me assume that EH1 proceeds as reduction, right? EH1 proceeds as reduction and EH2 proceeds as oxidation, let's say. So the EH would be equal to EH1 minus EH2, right. So, let us try to plug that in here. So, that would be equal to EH naught of 1 minus RT by N1F into natural logarithm of Q1 dash, right, minus EH2 naught minus RT by NF N2F, N being the number of electrons being transferred in the half reaction, let us say. So, in this case, if it is the same number of electrons being transferred, let us say N1F, right, into natural logarithm of Q2 dash, right. So, what do we end up with here? It is going to be equal to EH1 naught minus EH2 naught minus RT by NF and natural logarithm of Q1 dash by Q2 dash, right, Q2 dash. Yes, would that be the right way to express that? Yes, I believe that is true. And how would that transform into? That is going to be equal to EH1 naught minus EH2 naught minus RT by NF natural logarithm of Q of the overall reaction, right, Q of the overall reaction, right. So, when is this particular value going to be positive now, right. So, this Ecell would be equal to delta of EH naught minus RT by NF, RT by NF natural logarithm of Q dash overall, right, Q dash of the overall half reaction now, right. So, here let us say if it is not only N, what do we say, the same number of electrons being transferred as in one half reaction if we had N1 and then N2. So, the N would have to be replaced by N1 N2, right, the number of electrons being transferred, and Q dash 1 and Q dash 2 would have to be the ones when you multiply, let us say, Q1 dash by N2 and Q2 dash by N1, right. So, we are looking at the case as in, let us say, for the Q1 dash relevant half reaction we had N1 electron transfer, and for the Q2 dash relevant reaction we had N2 electron transfer. But to have the same number of electrons being transferred, we need to multiply Q1 dash by N2 and Q2 dash by N1, right. So, then here the N would be N1 N2, and the relevant Q1 dash and Q2 dash should be modified such that you multiply Q1 dash by N2 and Q2 dash by N1 and the relevant stoichiometric coefficients, I guess, right. Anyway, so that is one particular option here, not option, pardon me, the way to go about it. So, obviously, when if Ecell is greater than 0, then what does that mean now? Then the electrode 1, let us say, is cathode, right, or where reduction occurs, right, and electrode 2 is the anode where the oxidation occurs, right, as in EH is higher, EH1 is higher than EH2, right. So, again we can understand this in terms of what we had, the half reactions we had earlier, the relevant setup here. So, here EH1 is higher than EH2, right. So, again what do you see here? That would mean reduction with respect to this couple and oxidation with respect to this couple, right. So, again the relevant cathode and anode out here. So, again that is one particular case to go about it. So, obviously, if Ecell, right, is less than 0, what does that mean now? Then the reverse needs to be applied, right. Then what do we see now? 1, right, is going to have to be oxidation, right, or 1, the electrode cell 1 would have to proceed as, or it would be the anode, and 2 would be the reduction, let us say, right, and that would have to be the cathode if Ecell is negative, I guess, right. So, this is one particular case though. So, but the major aspect is, let us say I have an unfavorable reaction or the Ecell turns out to be negative now, let us say, right. So here let us say we are talking about redox potentials, right, and electrochemical cells, and we looked at the electrochemical cell calculation and saw that let us say when EH1 greater than EH2 we looked at reduction and oxidation, but let us say if it is less than 0, let us say we say that it is unfavorable or that oxidation should take place at anode and reduction at cathode. But let us say if I want to force a particular reaction to proceed as reduction, even though the thermodynamics or such let us say that it is not going to proceed as the relevant what do we say redox process, I guess. So what can I do now? So in that context obviously I can impose an external potential now, right. So I am going to say I can impose, right, a potential or a external potential, right, impose let us say an external potential. By imposing this external potential I can turn this Ecell which is less than 0 right now, right, so that 1 proceeds as oxidation and 2 proceeds as reduction, right. By imposing this particular what do we say external potential, I can see to it that Ecell plus this external potential that I am applying will turn out to be 0, right, and in that case again you are going to have reduction at your particular electrochemical cell 1, right, which will then be the act as the cathode, right, and oxidation here. And again what are the applications? Obviously if there is a compound let us say that you want to reduce and under thermodynamic conditions it is not going to be reduced now. So you can have these external potentials applied to be able to force these particular what do we say reactions or half reactions or the redox reactions to go through. And let us say practical applications, what do we look at? We look at chrome plating, I guess, right, chrome plating, right. As in what are we trying to do? We are trying to plate the metal onto the electrode, right, and as in Cr3 plus we want to make this favorable, which is usually not, right. So for that let us say we apply the external potential. So how do we go about chrome plating, or someone refers to chrome plating, right. I want to be able to reduce Cr3 plus to Cr naught or with the neutral charge let us say, right, and let us say this reaction is not favorable though. So how do I go about that, or how do I make that happen? I make that happen by imposing a external potential now, right. So again there are again applications with respect to these particular aspects, but here with respect to understanding the system let us say with respect to Ecell, right, and the external approach, people I guess need to look at the terminology or the relevant science involved now. So here as in to which particular electrode would you connect the positive terminal, and to which particular electrode would you connect the negative terminal, and so on. So again we are going to look at these aspects and then look at also ORP measurements, right, as in ORP measurements as in to be able to get what do we say generic overview of the reduction potential, right, oxidation reduction potential of a particular solution. You have these ORP meters that you can use. I mean there are some applications but not a great lot. So we are going to look at or in greater detail with respect to these terms respect to or with respect to the science with respect to the external potential, and also look at with respect to the ORP measurements, and then move on to let us say understanding how corrosion happens and how you can limit corrosion in the next session, I guess, right. So I guess with that I will end today's session, and thank you.